Good morning, everybody. My name is Pietro Carrara. I'm a PhD student from University of Milan, and I work in a laser laboratory called Sprint, which is hosted in Trieste, close to the electrosynchrotron, which is within the NFFA European project. The main framework of my PhD project is the study of new ways to manipulate the magnetization state of materials and of devices. For example, for writing the magnetic bit in an MTJ. To do so, the application of an external magnetic field is not the only possibility. There is a lot of research nowadays, for example, for the employ of electric fields in multiferroic materials or devices, metal structures, or, for example, for employing laser light, thermal gradients. In my case, I study the interplay of the magnetization and of the strain in the materials. In particular, we employ acoustic waves, so a dynamic strain, looking for surface acoustic wave-driven spin waves. Indeed, if we look at the dispersion relation of surface acoustic waves and of spin waves, we see that they are basically degenerate in the few gigahertz and few inverse micron range. So we can tune an external magnetic field and find the condition of resonance between the two degrees of freedom. The main actor at play here is the magnetoelastic coupling, mostly the magnetostriction. So we start our research in this field looking into a very simple sample, which is a ferromagnetic nickel thin film deposited on a transparent substrate. The technique we used is based on the transient grating spectroscopy technique. Basically, we have two ultra-fast sub-picosecond pump pulses, which are sent on the sample, and they interfere, generating a pattern of interference stripes. Then the sample locally heats up, and its thermal expansion generates acoustic waves in the material. Third beam, the probe, is sent on the sample and can be diffracted by the acoustic wave present in the material. These are the data we observe. We have the intensity of the diffracted beam as a function of the time delay between the pump and the probe. And we see these oscillations, which are directly linked to the acoustic wave present in the material. We can fast Fourier transform this trace, obtaining observing the presence of two peaks. One is the Rayleigh surface acoustic wave, and the other is basically the bulk longitudinal wave. In this setup, we can change the wave vector of the acoustic wave by changing the impinging angle of the pump beams. This way, changing the periodicity of the interference stripes. Now we can add a magnetic sensitivity by adding a magnetic field and by changing the probe, which now is sent on the axis of the setup, and we observe the Faraday rotation of the transmitted beam. These are data that we observe. We can see that by changing the external magnetic field intensity, we can see waves, acoustic and magnetic waves, at different frequencies, which are basically the same as the acoustic ones we observed before. So we can conclude that we are observing phonon-pumped magnons. By performing a sweep of all the magnetic fields, we obtain maps like these. On the left, we see the time domain traces in color code. as a function of the applied magnetic field. And on the right, we have the fast Fourier transform of the previous map. Here we can see that for precise frequency and applied field conditions, we observe a clear resonance behavior. The frequency are exactly those observed in the purely acoustic experiment. We understand this data in the framework of ferromagnetic resonance. To start with, we can say that the core, the essence of magnetization is angular moment. And so it doesn't surprise that the basic equation governing the dynamics of magnetization involves precession, it is the Larmor precession, plus a term which is called the Gilbert term, which gives the damping of this precession and the final alignment of the magnetization on the magnetic field axis, on the equilibrium axis. Now, if we add a radio frequency field tuned at the proper frequency, we see that after an initial transient, then the magnetization starts to precess on a stable orbit. This is precisely what ferromagnetic resonance is. There is no limitation on the nature of the radio frequency field we can apply. In standard FMR, it is an electromagnetic wave, while in our case, it will be the magnetoelastic field due to the surface acoustic waves in the material. So in this framework, we analyze our maps by finding out the frequency and magnetic field of the resonance peak and the full width at maximum. Frequency and resonance field are linked by the so-called Kittel relation, which dictates the dependence of the resonance frequency, of the magnetic resonance frequency on the magnetic field. The full width of maximum is in a linear relation to the resonance frequency, and the slope is proportional to the alpha parameter, which is, recalling back, the term responsible of the viscous damping torque. The intercept is called delta H inhomogeneous. It's called inhomogeneous broadening, and gives information about the local inhomogeneities on the sample. So we analyzed our data with different wave vectors, different angles of the pulses, and performed a quantitative comparison to standard FMR performed on the very same samples. These are the results. We observe here the frequency versus resonance magnetic field in blue for our setup and in red for standard FMR. We see that there is a good agreement between the two techniques, and we can extract from the fit the effective magnetization, and the two values obtained with the two techniques are in good agreement. Here on the right, we observe the full width of maximum as a function of the resonance frequency, and we see that there is actually a discrepancy mostly in the value of the intercept of the inhomogeneous broadening. We can understand this discrepancy thinking that in our laser-based technique, we are investigating a region of the sample which is as small as the focal spot, which is basically 40 microns, while standard FMR is an area integrated technique. And in that case, large-scale inhomogeneities come into account and enter definitely in the inhomogeneous broadening. Also, the values of alpha are different of the Gilbert damping, and even if they are basically compatible within the error bars. Nevertheless, it makes sense that the alpha obtained with our technique is smaller, because we are sustaining the magnetization precession well beyond its natural damping, its natural lifetime, because it is sustained by the acoustic wave. And so this is probably the reason why we observe a smaller value for this effective Gilbert damping. To have a final observation of our technique, we can look in this figure, our data, which are these black dots, and observed in their natural phase parameter, which is spanned by the resonance frequency, the resonance magnetic field, and the wave vector. We can project this data on the frequency wave vector plane, and we see that we observe the linear dispersion relation of the acoustic waves. We can project them on the frequency magnetic field plane, and we observe the Kittel curve, so the magnetic resonance curve. Nevertheless, it is important to stress that our technique is able to investigate the magnetic dynamics also on the wave vector direction. And this can be interesting for studying specific wave vector dependent phenomena, which are, for example, important in the study of the dissipation of the magnetic precession. In particular, it is known that a strong dissipation channel for ferromagnetic resonance is the so-called two-magnon scattering. Basically, the uniform precession, so the wave vector equals 0 mode, has a strong cross-section for decaying to a non-uniform spin wave mode, provided that there is energy degeneracy between the two states, which is the case here. For example, the uniform mode is degenerated to a non-uniform mode, and so there is a strong channel of decay from the one to the other. Our technique can be useful in this kind of investigation. For this, we are now moving to study magnonic crystals, where there is an intrinsic wavelength in the physical sample, and this can be interesting to be studied with our wave vector selective technique. I finished, and I thank you for your attention.